This video continues the topic of relational design, talking specifically about multivalued dependencies and fourth normal form. I know I've reminded you many times about relational design by decomposition, so let me do it very quickly. The designer specifies mega relations with all of the information they want to store and properties of the data. The system decomposes the mega relations into smaller relations that have good properties, no anomalies, and no lost information. When we have functional dependencies as our properties of the data, we get Boyce-Codd normal form, and then when we add to the functional dependencies multivalued dependencies, we get fourth normal form. And the specification of multivalued dependencies and the decomposition into fourth normal form is the topic of this video. As a reminder from earlier, fourth normal form is stronger than Boyce-Codd normal form. So if we have here all of the relations that are in Boyce-Codd normal form, some subset of those are also in fourth normal form. When we have functional dependencies, we can guarantee Boyce-Codd normal form, and then when we add multivalued dependencies, that's what allows us to narrow down to the stronger property of fourth normal form. So let's start with an example. We have information about students applying to colleges. The student is identified by the Social Security number. They may apply to several colleges, and in this video we're not going to have college states, just college names. We'll assume they're unique. And then the student may have hobbies. And they may apply, as I said, to several colleges and have several hobbies, but let's assume for now those are independent. So do we have any functional dependencies for this relation? Actually, we don't have any at all. The Social Security number does not determine the college name or the hobby or anything in the other direction. With no functional dependencies, the only key for the relation then is all attributes of the relation. So is this relation in Boyce-Codd normal form? As you might remember from the previous video, Boyce-Codd normal form says all functional dependencies have a key on the left-hand side. Well, since we have no functional dependencies, then the answer is yes. It is in Boyce-Codd normal form. On the other hand, do we think this is a good design? I'm going to say no, this is not a good design. Why not? Well, let's suppose that somebody applies to 5 colleges and they have, say, 6 hobbies. Then to have all combinations of colleges and hobbies, that would yield 30 tuples in the relation, and clearly that's not a good idea. We'd rather separate the colleges and hobbies if they are independent. So the separation of independent facts is what fourth normal form is about. And now let's get a little bit more formal. Like functional dependencies, multivalued dependencies are specified based on knowledge of the real-world constraints on the data being captured, and all instances of a relation with a multivalued dependency must adhere to the dependency. Now let's define exactly what a multivalued dependency is. For a relation R, we write a multivalued dependency using a double-headed arrow, and we say A multi-determines B, in this case, again, with A and B possibly being sets of attributes. So that would be A1 through AN and B1 through BM, which I'm abbreviating with A bar and B bar. So now let me write the formal definition of A multi-determines B, again using first-order logic, similarly to what we did with functional dependencies, but this one's a bit more complicated. It says, for all tuples T and U that are in relation R, if T with the attributes A of T equal U for the attributes A of U, again these are lists of attributes, so if the two tuples agree on their A values, then, and remember for functional dependencies it was simple, we just said they agreed on their B values, but now it gets more complicated. We're going to say that there exists a third tuple V in R that has the following properties. V has the same A values as T and U, so V sub A equals T sub A. Furthermore, V has its B value, okay, drawn from T, so it's equal there. And finally, it has its rest, so those are all the attributes other than A and B, equal to U rest. Okay, so that's a mouthful, but let's look at that pictorially. So here's our relation R, and we'll have the set of attributes A, the set of attributes B, and the rest of the attributes. And now let's make some tuples. So let's say that this is tuple T and this is tuple U. And we said that T and U agree on their A values. So they have the same A values, and then they don't have to have the same B values. So we'll call the first one B1 and the second one B2. And then for the rest, we'll call this R1 and R2. So what the multivalued dependency says is that we have a third tuple, V, and V again has the same A, and it has its B value from tuple T, so it has B1, but it has its rest value from tuple U. So then it has R2 here. So again, what we're saying is that if we have these first two tuples, T and U, then we also have tuple V. Now let me do something a little tricky. Let me swap the roles of T and U and show that we also, with this definition, are guaranteed to have a fourth tuple, and we'll call that fourth tuple W. By swapping the roles of T and U, W has again the same A value. Now it will take its B value from U, and that will give us B2, and we'll take its rest value from T, and that gives us R1. So what we can see here is that when we have the first two tuples that have this particular combination of B values and rest values, it tells us that we must have the other combinations as well. We must have B1 with R2 and B2 with R1. What it's really saying is those B values and the rest values are independent of each other and will have all combinations. So that might get you thinking back to our colleges and hobbies. Incidentally, sometimes multivalued dependencies are called tuple-generating dependencies, and that's because the definition is about having additional tuples when you have some existing tuples, unlike functional dependencies, which just talk about the relationships among existing tuples.